Okay, so today we are going to talk about series and eventually infinite series. A series is like a sequence, except we add all the terms of the sequence up. So if my sequence was 1, 2, 3, 4, 5, my series is 1 plus 2 plus 3 plus 4 plus 5 plus etc. It goes on forever. If this one happens to diverge or be divergent, meaning it's not going to go to a single number. This series, however, will go to a single number. Even if we go on forever. Oops, I missed something. I missed plus 1/2. Okay, that one will converge to a single number. I believe that number is 2. Um, so we have some shorthand notations, and it's called summation notation. So I'll write the sum notation. This little symbol, it's a Greek capital letter Greek sigma. And we could say let's sum the first 20 of these. That's going to be a little bit of a pain in the butt. Now this one right above it, this one is this sequence or series where I have to add up plus 1/2, plus 1/4, plus 1/8, plus 1/16. Um, so in general, you have with sigma, you have k equals, could be 1, could be 2, could be 0. You can't have 0 if you're going to use it to start at 0, if you're going to have a denominator that would potentially be 0. And it equals some value up here. And then you have some formula here. Okay. So we're going to do a few sums. This is exploration 1, summing with sigma on page 742. This is, series. This is series. This is 9.5. So here we're only summing the first 5 terms using this formula. Okay, the first term is I plug 1 in for k, I get 3 times 1 is 3. I'm going to keep doing this until I get to 5. So now I count up by ones, count by integers always. So k equals 2. So 3 times 2 is 6. K equals 3 is 9. K equals 4 is 12. K equals 5 is 15. Okay, and I'm done there. So now I just add them up because I've gotten to 5, I stop at 5. That's what the value on the top tells me. So this is 45. My little shortcut trick here was these two add together to be 18. It's 2 numbers, so I'll divide it by 2. These two also add to be 18. All of those are 9. Got essentially 5 numbers that average to 9. 5 times 9 is 45. Do this next one. That's going to lead to the development of a formula for an arithmetic series. Arithmetic, remember, means adding the same thing each time. This was effectively adding 3 each time. This next one is not arithmetic or geometric. Start with plugging in 5, 25, square at 36, 49, 64. I need a calculator to add those up. That is 174. These are all what we call partial sums, okay, where we're adding up things part of the way. It doesn't have to be k, you can use a different variable. So n equals 0, cosine of 0 is 1. And n equals 1, we get cosine of negative, or of pi, which is -1. When n equals 2, we have cosine of 2 pi, which is the same as cosine of 0, that's 1. 3 pi is -1. 4 pi is 1. 5 pi is -1. 6 pi is 1. 7 pi is -1. 8 pi is 1. 9 pi is -1. 10 pi is 1. 11 pi is -1. 12 pi is 1. These add to 0. Those add to 0. These add to 0. The ones where they cancel out so regularly are called a telescoping series. And so this is 1. Because those all cancel out, I'm just left with that 1. If I do this for infinity, I don't know, because it's either going to be 1 or 0, depending on which term I'm at. My next one I can do to infinity. So sine of pi is 0. Sine of 2 pi is 0. Sine of 3 pi is 0. Oh, 0 plus 0 plus 0 forever is still 0. And this last one, they give you a hint on this to make it a decimal. So I start with 3 over 10, which is 0.3. 2 is 3 over 10 times 2 is 20. Nope, I wrote that wrong. 10 to the k. That's what I... 10 squared is 100, so 3 over 100 is 0.03. 3 over 10 to the third, 10 to the third is 1,000. 0.003. 3 over 10,000 is going to be 10 to the fourth. This is equaling 0.3333, aka 0.3 repeating, which is 1/3. Okay, so this one can go on forever, and it's all going to add up to, if I'm just looking at the fourth one, it's 0.3333, or the partial sum. It means the sum part of the way. If I keep going to infinity, it eventually gets to actually be 1/3. But until then, it's just really close. Okay, so we're going to talk about the sum of an arithmetic sequence. And I'm going to notate this just slightly different than the book. This is known as Gauss's formula. Um, Gauss is generally thought to be the greatest mathematician of all time. His name is Carl Friedrich Gauss. He was German. He lived in the 1800s. And he's famous for this formula. And the story goes, he was mouthing off in class, something that annoyed the teacher. So the teacher made him stay in at recess, and he told him he had to stay in until he added the first 100 numbers. 1, 2, 3. And Gauss walked up to the board and wrote 5050 and left. What he did was a little trick here. And this is the formula that essentially runs that trick. So what he did was essentially what I did on the first one. He paired things together. All of these pairs had to be 101. And he recognized that he was using two numbers, so you'd do 50 times 101. 5050. Because he was using pairs of numbers, there's 100 numbers, half of them. So n over 2, half of the numbers, first plus last. And that works for partial sums. They notate this in your book. They put the divided by 2 over the a1 plus a2. I don't see any reason you have to. And that's how they wrote that out. So, example 1, we're going to find some partial sums of an arithmetic sequence. A corner section of a stadium has 8 seats along the front row. Each successive row has 2 more seats. The top row has 24 seats. How many seats are in the entire section? Well, in order to use this formula, I need to figure out which row this one with 24 seats is. This is small enough I could count, but I don't want to, and sometimes it's not going to be small enough to count. So I'm going to use my arithmetic sequence explicit formula to find n. Okay. So I know a sub n is 24. A sub 1 is 8. My common difference was 2. I'm adding 2 rows each time. I'm going to subtract 8 from both sides. And then I will divide by 2. Add 1, and I get n is 9. So this is the 9th row. If I want the total number, I'll call that S sub 9, capital S for sum of 9 over 2, 8 plus 24. 8 plus 24 is 32. In this case, I actually do like the idea of dividing 32 by 2. In the last case, I didn't, so I'm kind of going to pick which one's a whole number. So which one do I divide by 2? 144 seats in this corner section in the 9 rows. So that's the sum of an arithmetic sequence. The partial sum of a geometric sequence, arithmetic sequences also arithmetic series tend to never converge. Okay. So we won't do infinite sums of arithmetic. For a geometric, the partial sum formula is this. You're just going to have to take my word that that's what it is, unless you really want me to prove it, but I don't think most people do. So here is my sequence in example 2. Oops. So I wanted some. First thing I need to do is probably write the formula. I know the first value is 1. Or is 4, not 1. My common ratio appears to be negative 1/3. So I notice I'm alternating. This is called an alternating sequence, or it'll become an alternating series where I'm alternating the signs. Again, this only applies to geometric. And there's lots of series that are not arithmetic or geometric, but those are the common ones. They're the most useful and the ones that have nice formulas. So we'll be using those. So, and this one, they're actually having us end at the 10th term. Actually, I think that's the 11th. That's the 11th term. So the reality is, though, I only need to know the term number. I don't need to know the 11th term. So S sub 11, my general formula was G sub 1 R to the N minus 1. So if N minus 1 is 10, N has to be 11. That's how I know it's the 11th term. A sub 1 is 4. My ratio is negative 1/3. It's important that I do use the negative here for the 11th. 1 minus negative 1/3. And I'm just going to use a calculator, and I will use all those parentheses. If you don't use the fraction button, you're going to need to do these. Like this. And when I do 1/3, I just do 1 divided by 3. I'll use parentheses on the top one, but I don't really need to on the bottom. And I get 0, 0, 0, 0, 1, 6, 9, 3, 5. I'm going to talk about doing this one to infinity, and I'll give you the infinite form. That's not necessarily an equals here. If we're doing infinite, now this is alternating, so I'm slightly above 3, but the next one is going to be negative, so it will be slightly below 3. Because R2 in the infinity, these only converge. This is for convergent ones. So convergent means I'm actually getting to a single number. So it means I'm adding something that's so small every time, or they're alternating, adding, then subtracting, adding, and subtracting. So you're getting to a single number. And they're generally getting smaller. Terms themselves have to be going to 0. But just because the terms are going to 0 does not mean the series will converge. Not all the time. A lot of the times it will. But what's happening is R to the N is functionally becoming 0. So 1 minus 0 turns into 1. So that whole term goes away. And I end up with this infinite formula. So S sub infinity the infinite sum of this one, I think, is 3. 4 over 1 plus 1/3. 1 plus 1/3 is 4/3. My complex fraction, I'm dividing my fractions. It's 4 over 1 times 3 over 4. My 4's cancel, and yes, I am left with 3. it was above it, but the next one will be negative, so S sub 12 would probably be slightly below 3. And we'll be converging on 3 coming from both sides, slightly above, slightly below. So if you're thinking about a graph, your points are going to be converging to that, your sums, etc., etc., closing in on 3. Example 3 says we're going to look at some partial sums of some series and see if we think they converge or not. So here's a series. So we're supposed to look at the first 5 terms, which are of the series, 0.1, 0.11, 0.111, 0.1111, and 0.11111. I think that's going to converge to 0.1 repeating, which is 1/9. My next series, I'm just going to write out the first 5. The book only gives 4, but 10, 30, 60, 100, 150. This is not converging. This is divergent or diverging. One, 0, 1, 0, 1. This is actually diverging. It's just between these two. So depending on which one, I can't have an infinite sum because it'll either be 1 or 0 depending on which term it is. So that is actually considered diverging. So summing with an infinite geometric series, we're going to use our S sub infinity formula. That means S to infinity terms. So this is example 4. So something I need to get here is A sub 1 or G sub 1 by plugging in 1. 1 minus 1 is 0. 0.75 to the 0 is 1. A sub 1 is 3. My common ratio is 0.75. So I get 3 over 1 minus 0.75. It's 3 over 0.25, which is 3 over 1/4, or 3 times 4. It's 12. So here my common ratio is negative 4/5. And G sub 1 equals 1. Anything to the 0 power is 1. So 1 over, that's a 1. 1 over 1 minus negative 4/5 equals 1 divided by 9/5. So this is 5/9. Okay, a couple more parts of example 4. See, I get this. My first term is pi over 2. My common ratio is pi over 2 as well. My common ratio being greater than 1 means this will diverge. So with geometric series, the absolute value of the common ratio is less than 1. It's convergent. So that could be negative, but it's got to be between -1 and 1. If the absolute value of the common ratio is greater than or equal to 1, it's divergent. So this is diverges. Which really means there is no sum. The more terms I add, the bigger it gets. Or sometimes the smaller it gets, but in this case, it's the bigger. This one, I can see I have a common ratio of 1/2, and my first term is 1. So the infinite sum is going to be 1, that's 1/2, over 1 minus 1/2, which is 1 over 1/2. Dividing by half is multiplying by 2, so this is 2. Okay? There's a few other uses for this, one of which is expressing a repeating decimal as a fraction. So this is really 0.234, 0.234, which I could express as a series as 0.234 plus 0.000234 plus 0.000000234, meaning I could write it as a sum of and it's repeating forever, so it's 1 to infinity. And the 3 zeros is, nope, not plus, it's got to be a times for a common ratio. I'm going to actually start this at the 0th term, because I just want it to be that. 1 over 1,000 to the n. So that is a series 0.234 times 1. Actually, instead of being 0.234, why don't I do 234? So that'll get rid of my decimal here. Because I don't want a decimal when I'm trying to write this as a fraction. So 234 times 1 over 1,000, the first power is going to be 0.234. Times 1 over 1,000 again gives me that. Okay. So in this fraction, 234 times 1 minus 1 over 1,000 equals 234 over 1 minus 1 over 1,000 is 999 over 1,000. No, I should have started at 0 with 0.234. So now I'll multiply the top by 1,000 to get 234 over 999. And then I can go ahead and reduce 26 over 111, because those are both divisible by 9. Okay, this is a pretty acceptable answer. 1 minus 1 over 1,000 999 over 1,000. Okay. One last little application. Quite a while ago, we had this formula for future value of an annuity. And I gave you a slightly different version of it, where I computed n out for you and I was also computed out for you. But if you're doing this yearly, this is pretty easy to see. So then n is just years and I is just, if you're doing it compounded partially per year, it gets a little more complicated. But so the first year, my sum is R. Put R. The end of my first year, I compound my interest once, and I get R to the 1 plus I. Okay. My third year, I put in R. I add it to the last year's was compounded once. The first year's was compounded twice. So at the beginning of year 3, I've just added this. Year 2's amount was compounded for 1 year, multiplied by 1 plus the interest rate. Year 1's was compounded twice, 1 plus the interest rate. So you can see that I have a series here of a geometric series. My first term is R. My multiplying by 1 plus I each time. That's why I'm getting 1 plus I squared is 1 plus I times 1 plus I. So my common ratio is 1 plus I. So if I plug it into my series formula, I get R. Remember, my series formula is A1, 1 minus R to the N over 1 minus R. 1 minus 1 plus I is my ratio, the power of N, over 1 minus my ratio is 1 plus I. To get rid of my parentheses on the bottom, I distribute my minus, which means minus 1 and minus I. Not mean to erase the I, but 1 minus 1 ends up being 0. Oops, wrong one. 1 minus 1 ends up being 0. And we do end up, it is a negative. We end up with, oh, I wrote that formula backwards. This is not the correct formula at the top. That's why I'm not going to get it. This is 1 plus I to the N minus 1. So we end up here with this. Over negative I. A negative, I can factor a negative out of my numerator's parentheses by turning it around. The one that they put in the book, they actually pull the I off the front. Which means I don't need the parentheses around it. Okay, that is it for section 9.5.